Polymorphism is one concept which most developers tend to have some difficulty really understanding in the first attempt. So I'm going to try and make it simple. As you can see on the screen, I have a bunch of LOL surprise wraps and I have Kinder Joys. From the outside look of it, they all look the same. They all look like LOL, Glam, Glitter covers, or the Kinder Joys definitely look all the same. But under the hood, if I actually try and open them and get to the toy, then I'm going to get a different toy in each of these Kinder Joys or each of these LOL surprise boxes. And now, what does that mean from polymorphism perspective is that imagine that you had a class and the class basically was surprise toy, or let's say the class was Kinder Joy. And in the class Kinder Joy, you provided some behavior which was get toy. Now, when you implement, or one of the other classes goes and implements the Kinder Joy class, and it says get toy, it doesn't really knows what toy it's going to get back because that's actually runtime dependent upon what instance of Kinder Joy it was. That's not known beforehand. It knows for sure that there is a behavior or a function or API named getToy that is available on Kinder Joy that can be invoked. And once we invoke that, we're going to get a handle to a toy. The toy is going to be an aeroplane, it's going to be a mailbox, is it going to be a fidget spinner? We do not know that upfront. Similarly, for LOL dolls, we don't know which doll we are going to get or which pet we are going to get. But we just know that there is a function which is unwrap and open, which are available. And once those two are invoked, we are going to get handle to those toys. Now let's start thinking about it from a perspective of something concrete. Let's go back to our car example, which we have been doing inside our classes video. And we talked about different types of cars. The cars can be a Nissan, it could be a Toyota, it could be electric, it could be a gas-powered car. So there were a lot of variations, but all the cars had some common functions which were available. The cars could accelerate, the cars could brake, the cars had a mechanism to turn right and turn left. So those behaviors were common. Now the actual implementation of those behaviors was going to be very different. And that was decided upon which instance of the car I'm currently working on. And to in a lot of places, I don't even care on which instance I'm working on. I just know the fact that I want to turn left and I can call turn left on a car instance to turn left based upon which instance it is. Under the hood, it could be doing a lot of different things to decide upon how it is turning left or how it's accelerating, how it is braking, or how it's refueling. Electric car may decide to refuel using a charger, while a gas-powered car may decide or may need to actually refuel using 87, 89, 91, 93 based octane rating fuel. Um, so let's look at polymorphism. I just hinted that sometimes you do not know that which object you're working on till runtime, but is that always true? Again, I use the word sometimes, not always. So here's a chart for polymorphism that you need to keep into mind. There is runtime polymorphism, but then there's compile time polymorphism. And compile time polymorphism can further be subdivided into two different categories: function overloading and operator overloading. Function overloading is an example where you can go forward and define multiple definitions of the same function. And it could be that the syntax of the function basically differs slightly because one accepts one type of argument, other does not accept a different type of argument. And here you can start thinking about the fact that we had covered functions that have default parameters. As a result, under the hood, they are behaving like two different functions which are present. So that's one example of function overloading. Second one is class hierarchy based function overloading, and we're going to see working examples of all of those. So your parent class, which is car, has a refuel function and is basically going forward and probably always refueling at a gas station. But then when you start writing electric cars, you override the refuel function to use the charger in your garage to refuel the car. And that's function overloading. Next one is operator overloading. And here you start thinking about is that, well, when one operator makes one sense when used in context with another keyword. Um, Now here, one simple example you can start thinking about is not equal to operator. So you have a variable and it could be a string, it could be integer, and you're just simply checking x is not equal to y, and it's all good. And we're going to see an example of it. But if you remove the space in between, suddenly Swift starts to error out because now it becomes x naught, which is that you're trying to unwrap an optional, and x is not an optional, so you start getting an error. So that's all is operator overloading on when same operator can actually mean different meanings based on which context is being executed. Runtime polymorphism, we kinda actually covered it, and these are the examples where you actually do not know at till runtime which object you are working with, and based upon which object is passed to you, you basically go upon calling the functions on that particular object, and the functions could do totally different things. Simple scenarios can be you present a screen to the user, and the screen lets the user go forward and choose on by swiping to left or right which direction in the video game their car is going to turn. You really do not know whether it's going to turn left or turn right. It totally depends upon the swipe of the user. And once the user swipes, you might be instantiating a totally different object based upon some conditional logic in your code, passing on that object instance to a different method, which just knows that it's supposed to call turn left or right on it, and then things will happen. Doesn't really knows which object it is that is covering. Now, since for virtual or runtime polymorphism, protocols are very important, and these are the pieces where we cover is that we define a contract which all the classes must follow, and that's how I know that as per the contract there is an accelerate function, there's a break function, there's a turn right function, there's a turn left function, because that's part of the protocol. And I know that all the instances who implement this protocol must implement this method, so I can safely call upon these functions assuming that they must be implemented is very important for achieving runtime polymorphism. We are going to first touch upon the topic of protocols. Now, what exactly are protocols? As the English meaning means, the official procedure or system of rules governing affairs of state and diplomatic occasions um, defines the protocol. What it means is that there are some rules that have been defined that must be followed. And the example here that has been provided is that um, protocol forbids the prince from making any public statement in his defense. So we know that if we are dealing with the prince, then he's not going to make a public statement in his defense. Okay, so that's kind of known because that's part of the protocol. Similarly, you can start thinking about HTTP protocol. The HTTP protocol now goes forward and says that fine, in all the requests which are going to send out, I'm going to have certain headers which are defined. Then I'm going to pass you what kind of actions that can be performed, whether it's a get, whether it's a post, whether it's a put, or it's an update. Then I'm going to have certain body. Okay, if it's a post, I will body. If it's a get, I will have some key value arguments which are passed, but I will not have a body. So all that is defined by the protocol itself. Once you know the protocol, you know what those meanings actually mean, like what does it get means. So let's start by looking into a concrete example of a protocol. Okay, enough theory. Let's see all this in practice now. So I have a playground page, polymorphism, and in the sources I've defined main.swift. And now is the time to go forward and define our example. We're still going to continue working with the computer language example we have been following for all object-oriented programming flow. Now, the computer programming language will have a behavior function saying do syntax analysis. And we want to enforce it. We want to have this function being called and defined by any implementing class. So if you have a Swift or your Kotlin or your Java, any computer programming language, you must provide an implementation of do syntax analysis. So that's a restriction from our end. Also, we want to provide another optional method saying do syntax analysis, which takes a boolean for optional. has the same method signature, just that it accepts an argument, and that may or may not be defined by the implementing classes. So Swift may decide to implement it, and Kotlin may decide that it's not going to implement it. Can go either way. So with this, let's get going. So we're going to start with defining a protocol, and the protocol is computer language protocol. And I'm going to define a function inside it, which was to do syntax analysis. So all done. Cool, sounds good. When I will try and use this protocol in polymorphism, it's not going to work, as you would have seen in our inheritance video, that you need to have the right access specifiers. So let's go forward and define a public access specifier for the protocol. Protocol doesn't necessarily need initializer, so we're good there. Now, everything that you're going to define in this protocol is going to be required. In Swift, every method defined, any function defined in a protocol is a required function. So when I define the second function, which I'm defining for method overriding, I'm going to define it, but with same syntax, just the function type is going to vary because it's going to take a parameter saying is optional, and the is optional parameter is going to be Boolean. That's the only difference. Now, when I go back to my actual Swift Playground page and try and define a class, and the class I'm going to define is computer language, which is going to implement the computer language protocol. I will definitely get an error, and I will get the error because it says that okay, you do not implement all the required methods to find the protocol. So I go back to my main.m. From the protocol, I find the method definition that I need to implement. I copy it and I go forward and implement it. And for the example, we're just going to have a print statement inside it saying that doing required syntax analysis. Okay, so done. The problem is that I'm still going to get an error saying that okay, I'm not still implementing the protocol, or all I'm not conforming to the protocol. And what it means is that there's another required method which is actually missing. And the method which is being complained about is the other method. Well, I wanted it to be optional, but I didn't tell Swift that it's can be optional. Now there are two ways of doing that. In Swift, like I said, okay, everything which is defined inside the protocol is required. And there's a separate video on protocols also on abstraction where you can go forward and see how to do that, what's the way around it. But that way has a pitfall, which I also talk about with dynamic dispatches being done. So I'm gonna not discuss that mechanism here just to prevent redundancy. But I'm gonna import foundation because foundation provides you Objective-C declarative. So I can say that okay, this class which I'm defined, this protocol I defined, is now available to Objective-C as well. And when I do that, Objective-C did supported optional parameter. So since the optional or the Objective-C runtime is now available to me, I can start using those optional and the required parameters. Required is only for init, so I'm gonna skip that. By default, it's going to be required, but I can define optional. And I say that okay, syntax analysis is optional. Now when I come back in here, it does not errors out anymore because this other method is now optional. But again, I do not recommend this approach if your framework or your code is also because why introduce Objective-C runtime if you don't really need it. Check out another video to show you how to bypass it. For now, let's say these are the two methods which are defined. I implemented the do syntax analysis. Now I can go forward and implement the other optional method as well, which is again to do syntax analysis but optionally. So I will just say doing optional syntax analysis. Okay, all good. Now when I call my computer language, I can see that it has do syntax analysis, and computer language also has do syntax analysis with optional parameter being passed to it. So it has both options available, and I'm going to say true. So you will see, okay, it can execute, it can print required and optional, all good and dandy. Now, going back to the slide deck, this is what we were talking about when we said is compile time polymorphism. So we can do compile time polymorphism. This example of function overloading. I've overloaded the function. There are the name of the function is same to syntax analysis, but the function types are different, and I have done function overloading here. Another example of doing the function overloading in compile time polymorphism is that I can have a child class. So I can define a Swift as a child class to computer language, and I can decide to implement the syntax analysis again, but this time it's very Swift specific, right? So I can go forward and call here Swift dot do syntax analysis, and I'm going to remove this second line in the middle so as to avoid any confusion. Now, when I start looking at the results, what you would see is, first of all, it knows that uh, it's a child. Its parent class also defines a similar function, so you just can't and go forward and use the same signature. And this is to prevent mistakes where programmer accidentally chooses the same name as the parent class. So you override to say that yes, I intended to override the parent class function, and you do that, and now it works fine. But you can see that Swift basically calls the child as expected, and this is an example of compile time method overloading as well. So both examples, whether you define two methods, same name with different function types, or the parent class and the child class defining the same method with the same function type, both are examples of function overloading. The next example of course is for operator overloading, and in the I will actually cover that in a bit, but here I want to touch about is the runtime polymorphism. Now we talked about this runtime polymorphism which exists. So let's see how it works. The way it works is that let's go forward and simply remove these two calls. So there are no calls happening right now. I am going to define a variable random, okay, and it's going to be type of integer, okay, and it's going to define a random number in the range of 1 to 100. Okay, let's just fix the range operator, which is why it's complaining about. So I'm going to use a half range operator, okay, and that's going to fix the main issue. So I'm going to generating a random number every time I run it. I'm going to get a different random number. I'm going to put a simple condition here. And before I do, let me go forward and say that I have to have a comp language which is going to be of the type of the protocol which I defined. So I'm not defining a concrete type. I'm using comp-lang protocol, which is the protocol. So I have defined saying that okay, this variable of the type contract. I don't even know which instance actually or which class actually implemented this protocol at this point in time. And then I'm going to go around and write my happy logic, and it's going to be something like if random is less than 50, okay, or if random, okay, is divisible by 2, okay, so if it is divisible by 2, then go forward and say that comp language is of type Swift, okay, and let's just go forward, and instead of just calling the parent, I'm going to define another class for Kotlin and say that okay, give me syntax analysis for Kotlin. And here I'm going to say that if it is not divisible by 2, then I'm going to have comp language which is of type Kotlin, just random logic which I'm writing. And then I'm going to call comp language to do syntax analysis. Okay. The point is when I compile, I knew that the comp language is a variable which adheres to the comp lang protocol. That's all I knew. I don't really know what happens each time I execute it. So each time I execute it, I'm getting a different number. First time 99, now 67. Both were odd numbers, so every time I executed it, I was able to get back um, result which was of the Kotlin. So now it's 47. So for some reason, all the numbers are coming out to be odd till now. Now I get an even number. But the point is that in each run, I could be reading from the database based on user input, based on some network configuration, at runtime, there's logic which is getting executed and decides that this comp lang variable is of what type. And then we just know that on this contract, I can call do syntax analysis, but the real object on which syntax analysis is going to get called, whether it's Swift or Kotlin, is decided at runtime. And this is example of runtime polymorphism.